Welcome back, Adventers, to my channel, and we are solving Advent of Code 2024. And today I'm presenting you from a icosaedron, which is a 24-side polygon. Yeah, if you pause the video here and zoom into the camera frame around me and count the sides, this will have 24 sides because today we are solving day 24 of Advent of Code. And yesterday we solved the LAN party where we had to find the biggest connected network of all the computers in a LAN party. And we learned how you can solve an NP hard problem, which usually takes exponential time, in still a reasonable enough time if you optimize it and constrain the scope a little bit. And yeah, if you're new here, I am Jatin Kumar Malik. I'm a principal software engineer who absolutely loves solving these puzzles. Last year, I did a blog post series on Medium, and this year, I'm doing YouTube. And if you haven't seen the action, you can catch up the last 23 videos here in this playlist. And with that, let's get started. So day 24 problem today is called crossed wires. Let's read it. So you and the historians arrive at the edge of a large grove, and that's a reference to 2022 day 23. And a grove is basically a clump of trees somewhere in the jungle. After the last incident, the elves installed a small device that monitors the fruit while the historians search the grove. And one of them asks if you can take a look at the monitoring device. Apparently, it's been malfunctioning recently. The device seems to be trying to produce a number through some Boolean logic gates. Interesting. I think the day before yesterday, I think we have seen the exclusive or XOR or XOR gate in a couple of questions. I will link them here for you. But let's read on. And each gate has two inputs and one output. The gates all operate on values that are either true or false. And then we are given three gates. So we have AND gate, OR gate, and XOR gate. So before I read further, if you're new to computer science, so all of the modern computing that you see, they operate on logical gates. So what do they mean? So we have primarily a few logic gates, and we are given an example of three gates here, which is this AND, OR, and XOR. And if you see a modern processor, a CPU, and if you zoom into it at like a nanoscale, nanoscopic level, you would notice that a CPU is made up of a lot of transistors. And a transistor can basically store a value which is either 0 or 1, which means either it is in an off state or it is in an on state. And then using this transistor and bunch of these logical gates, we can do a lot of operations. And in computer science engineering, it is one of the very common things that you learn, even in your high school, where you learn how to create a basic adder, subtractor, multiplier using these logical gates. But talking about these gates here, so we have AND gate that looks something like this, where it takes X comma Y and it outputs Z. And in computing, you can represent this by AND, like if you're using Python, or like AND sign. The OR gate looks something like this, if I'm not wrong. It's been so many years since I made these. And the OR gate is represented by a pipe in your programming language. And then there is XOR or XOR, which is the exclusive OR gate. And this looks like OR, but there is an extra bar here. And then you get the Z out. And exclusive OR is represented by this caret sign. And explaining these, so AND basically means that if your both input are 1, it outputs 1. And if the either input is 0, these gates will output 0. And the OR means that if the output is 1, if one or both output is 1, so either or, like any output, if it is 1, the output will be 1. And exclusive OR is just the exclusive of OR, which means that it will only output 1 if the inputs are different. And if the inputs are same, these gates output 0. And what I'll do is I'll just link a truth table for all three gates right here for you to see and understand that. And these are basically the building blocks of modern computing science. Everything around you that you see that has some kind of a processor in it, be in your fridge, your TV, your modem, monitor, phone, computer, everything. They are using a bunch of logical gates beneath the surface. But let's read on. So the gates wait until both the inputs are received before producing output. Wires can carry 0, 1 or no value at all. So this is interesting because there is something called as a null value or a none value. So we can have three kind of values. And there are no loops, so there is no loops going on. Once the gate has determined its output, the output will not change until the whole system is reset. Okay, so once you start running a system, we will have output and you will keep those outputs. Each wire is connected to at most one gate output, but can be connected to many gate inputs. So it's a series of gates that are given where this output can then become input for something else, and another very common pattern. Rather than risk getting shocked while tinkering with the live system, you write down all of the gate connections and the initial wire values, your puzzle input. So we are given some initial wire values. So you can consider them in relative safety. For example, so we are given this example. Let me copy it here so that we can take a look at it. So we are given a bunch of values for x 000102, y 000102, and then we are given a bunch of operations that is giving us value of z00, z01, and z02. So because the gates wait for input, some wires need to start with a value. Of course, like the system needs to start somewhere, which is the inputs to entire system. The first section specifies these values. For example, x001 means that the wire name this. Okay, so these are the wires that are given to us. And for example, and these are like the operations. And these are like operations that we are doing, logical operations. Okay. And it says that here it says 00 and y00. So if I change my color, so x00 has a value of 1, and so we will write 1, and the value of y00 is 0. So we just talked like if 1 and 0 happens, like both of the output needs to be 1, else the answer is always 0. So answer would be 0. Similarly, x01 XOR y01. So x01 is 1 and y01 is 1. So it is doing 1 XOR 1. And in exclusive for, we just read that it will only give the output 1 if the inputs are different. If inputs are same, this will also output 0. So we get the output 0. And I think it probably is mentioning here, it's not. And x02 and y02 or, so 1 or 0. So 1 or 0, it means even if there is 1, 1, we will get answer 1. So basically these are the values where z00 is this is this, and then this is this. Okay. And I think this is what it's saying, that 02 appears on 00, 02 appears on z01, and 12 appear on z02. That is absolutely correct. And ultimately, the system is trying to do is produce a number by combining the bits on all wires starting with z. Okay, so these are our outputs, and you have to create a number out of these wires that starts with z. So z star, we will use a wildcard pattern. And z00 is the least significant bit, and then this and then so on. So in a binary number, whenever we are given any number, let's say 101111, this is called the LSB, which is the least significant bit, and the leftmost bit is called MSB, which is the most significant bit. And in this example, it says that when you are creating a number out of it, your least significant bit is z00. So this is LSB. And then based on how many numbers you have, the number of wires you have, your Zn, which is the MSB, would be this. So you will fill it in this way, where Z01, 02, and ... like so on. So if you look at this example, the number that we will be end up creating with this would be 100 and binary number, which is equal to decimal number 4. So you can convert a binary number to decimal number directly, either using an int function or binary function inbuilt into the Python. But essentially how it works, and I explained this in I think one of the questions before as well, is that like in a binary number, you just multiply. It is basically sigma of 2 raised to the power n, where n can be go from 0 to n, whichever is the value. And if you look at this here, there is 0, 1, 2, which means it is 1 into 2 raised to the power 2 plus 0 into 2 raised to the power 1 plus 0 into 2 raised to the power 0, which means 1 into 0, 0, 0 into 2, 0, plus 4, which means the answer is 4. And this is how you can also write your own function to create a binary number. And similarly, you can do the inverse and get like from decimal, you can convert to a binary number. So that's clear. And here we are given another larger example, which is very interesting, where we are given a bunch of initial values. So it seems like our initial wires are following the pattern with X star star and Y star star. So I'm using star star as wildcards, where you can see it's X00, X01, X02 to X04, and then similarly Y002, Y04. And then we are given a bunch of numbers that look very different, but we can also see there are a bunch of Y0s and X00s also there. So I think I see where this is going, but it says that after waiting for all the values on the wires starting with Z, the wires in the system will have following value. Oh, so this is basically a network of these logical gates that are given, that where if you try to denormalize it and you try to write it sequentially starting from the wires that we have numbers, it seems like look at here. So Y00 and Y03 becomes DJM. Similarly, Y03 or Y00 become PSH. So if we denormalize this network and run this network, at the end, each of the wires in this system will have these values that are given to us. So 1, 0, 1, 1, 1. But at the end, all we care about are the values that are starting from Z, basically starting with the Z, which I also mentioned here, which we have to use to construct a number. So in this example, that is here, if I align this whiteboard well, we can see that combining these bits from all wires starting with Z produces the binary number. So it's 0, 0, 1, 1, 1, 1, 1, 1, and then 0, 1, and then 0, 0, 0, 0. Is that correct? And then there's another 0 because here, yeah. So 0, 0, this and this, how I'm calculating this is I'm reading this backward. So this is Z0, 0, and this is Z1, 2, this number, which is the MSP and LSP. And now similarly, using the technique that I told you here, where you can just multiply this with the 2 to the power position of this, starting from 0 here and then going to end here, we can see that the decimal number this produces is 2024, which is also our current year. That's very neat, actually. So now the question is saying that you have to simulate the number of gates and wires that are given to us in our puzzle input, and what decimal number does it output on the wire starting with Z. And if I see my puzzle input, you can see that we are given some bunch of initial values starting from X00 to X44 and similarly Y00 to Y44. And then we are given like a huge network of logical gates and operations that they are doing. So after we let this system run, at the end, it will produce some values of Z. And then using that, we have to get the decimal number. And that is our answer of part 1. So with this, I hope the question is clear. It's very clear to me. And yeah, so now is a good time for you to pause and think how you will approach this problem programmatically to do this. And this is a very interesting problem. And yeah, once you're back, I will share some of my hints and approach to get you started. I will see you in a bit then. And all right, so if you're looking for some hints, let me grab my orange marker here and let's talk about it. So in this question, I think one of the initial states that I wrote like the common hint every time is the representation. So I think you need to think about how would you represent these wires here, the gates and their outputs. And this is, once you figure that out, I think 90% of your problem is solved automatically, because once you're able to solve the wire gates and their outputs and how to store the connections between them, your question is essentially done, because you just need to then find the output of Z wires and then calculate your answer. And since the gate can only produce an output once it has both inputs sorted, you need a way to somehow keep a track of what are the gates that are now ripe for you to process and get a new output. And then maybe this output becomes your input for some other gate G2. And this is an initial interesting state management kind of a diagram where you are just maintaining different states, and till your leftmost inputs are processed, you cannot directly jump onto another gate on your right side in a way. And looking at the question, I think the order of operation becomes important. Like you have to pay a very close attention to the order of operations, and how you would serialize them is the key to solving the question. And I think here, some of the approach that you might consider involving is that we first need to, of course, parse the input that is given to us. And you need to find a data structure to initially assign the values to the initial wires that we are given. And then you need to do a bookkeeping of all the other wires that will finally receive some output, which is given to us here. And I think one of the initial simple approaches, like if you don't want to optimize anything, of course, there is a brute force way where you you represent all of these operations in an array, and then you just maintain all the input values in some dictionary. I think that is a good option. Please don't go around assigning these many variables manually. And then you can just iterate on top of so let's say there is these gates operations. So you can just assign each of this entry that is given into a gate, and then you can just iterate multiple time till you don't have any gate where your input and output are not available. And then you can just maintain like a dictionary of all these key value pairs where all of the wires that you see here on the right side, they all should have some value. And once you have that, then you parse out all the z values from it. And then you calculate your answer by constructing from least significant bit to most significant bit and then converting it into a decimal. And I think that should definitely work. But there is definitely some optimizations that we can do here. So if you can imagine this whole problem into just a simple graph and then construct a graph, that will help you to just do it all in one iteration, because then you can serialize the order of these operations in which you should do them so that it helps you to do. And it's in a way, it's like there is a word for that. It's like a topological sort. Exactly. That is the correct word. And there was one of the days where we did the same thing. So if you could topologically sort this graph of operations, you will essentially have a graph which is going from left to right in the way that you are discovering the output. So instead of directly looking at, let's say, NTG, XOR, FGS here, you would initially look at all the values that you have available, which is X0, X and Y from 0 to 4, which means like something like this. The one operation here, X00, X03, you will look at this, 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 and this. And once you get this, you will start to get these values like NRD, NTG, FFH, and then you will look at these values and then so on. So in just one go, you can do that. And yeah, I think probably that is what I'm going to do. It seems fair to try to do that. So yeah, probably you should pause the video here and now go back to your code pad and try to solve this, the given example manually with your paper and pen, and then try to see how you will convert this into a logic. And you're converting logical gates into a logic, pun intended. And I will do the same. And once I'm back, we will discuss in the retro, like what changes I made, if any. But this approach seems to be pretty much apt for this one. And yeah, with that, all the best. I will see you in a bit. Hey, welcome back. As you can see, we have finished the part 1 and received our first gold star. And we are closer to finding the chief historian. And I did exactly what I discussed here. And for fun, I basically did both the brute force approach that I was talking here, and I did the other one, which was the topological sort approach, just for fun. But actually, our puzzle input was not that much, and I did some benchmark. And if you can see here, there is not much difference between the runtime, as it is really, really fast. I think it is at the 100th of a second difference between both of them. So yeah, and we were able to get our answer fairly quickly. And in the brute force, as I discussed, I just iterated over my functions again and again. And once I stopped processing any outputs, I just set up a small flag. I just broke out of the function and then just got all the z values and did that. In topological, I first did some pre-computing to topologically sort all the gates, and then just in one pass, I did all the iteration. This is definitely the better way of doing things, but today was the way where brute force worked really well for the part 1. So with that, let's move on to part 2 and see what's that about. But before that, Hey, if you're finding these walkthroughs helpful and are enjoying our coding adventure together, smash the subscribe button below and join this awesome community. And it's absolutely free. I have zero snake oil courses. I have absolutely nothing to sell it to you. And if you subscribe, you will basically get notified for every video that I make. And I have a few videos in pipeline where I want to share some deep insights from my 15-year-old long career. So it should probably be helpful and you might get to learn a thing or two. But yeah, with that, let's go back to the part 2 and let's read it. Part 2, I'll pick up a color. So it says that after inspecting the monitoring device more closely, you determine that the system you are simulating is trying to add two binary numbers. And interesting, this brings back so many memories of my engineering days where we implemented half adder and full adder, and you would know what I'm talking about if you took some of those classes where you would create that, where a half adder is the one where you give two inputs A and B, and then the half adder would give you two outputs where it will give you an output C, the sum S and C carry for that. And in a full adder, basically FA, you can give A, B, and C, where A and B are number and C is the carry, and then it will give you back a sum and a carry. And yeah, these are very interesting topics to look at. So I'll urge you to check this out. Google this after this video and read a bit about them. And your CPU has a lot of these adders already implemented. And this adder, if you zoom into these boxes, is nothing but a bunch of XOR and AND gates. But let's read the question. Specifically, it is treating the bits on the wire starting with X as a one binary number and treating the bits on the wire starting with Y as a second binary number, and then attempting to add those two numbers together. The output of this operation is produced as a binary number on the wire starting with Z. In all three cases, the 00 is the least significant bit and then 0. Oh, so I see. So remember we were given these inputs here. Let's take this example. So what it is saying is essentially it is just trying to do so x00, x1, x01 and x02, and then it is trying to add like y00, y01 and y02 to produce the value z00, z01 and z02 that we are doing here. And if you see this and try to write them down, so this number is 111 and we are trying to add it to 010. And there is an interesting thing, like, so in binary number, when you add two numbers together, it follows very similar to the binary number, but it is a little different. So like in decimal numbers, remember whenever your addition of two numbers goes over 10, you keep the carry and you move on to the next element. I think it's very similar here. So in binary, we have these, if we talk about the sum cases, we have these four cases where 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, but 1 plus 1 is equal to 0, and then you do like a carry of 1, which goes to the next value. So in this case, if we see and we try to do that, in this case, the answer in the part 1 was coming as 100, which was 4. But if I do this myself, I think that's what the question is saying. In all these cases, the initial value is just one instance. That sum gives the wrong value. So let's do a sum ourselves following the rules that I showed you here. So 1 plus 0 would be 1, and 1 plus 1 would actually be 0, which will carry over the 1 here. And 1 plus 1 would again be 0. 0 plus 0 would be 0, would carry here. And actually, the answer should have been 1001. And is this what it is telling us here? 0, 0 is significant? Nope. And if I calculate this, so this would be 1 plus 1, 2, 3, 8. So the answer should have been 9 here instead of being 4. So this was actually a wrong answer, which means that the logic that we were following here, this was not giving us the correct value. But let's see what we have to do in the question here. So it says that the initial value for the wires in your puzzle input represent just one instance of pair of numbers. So this is one of the test cases in a way that gives this wrong value. Ultimately, any two binary numbers provided as input should be handled correctly. And then this is probably like an edge case, as I mentioned, right? because you can see that here we did a sum of two 3-bit numbers, and this gave an output of 4-bit numbers. And if you don't understand what is a bit, I have this very small short explaining how these bits work and what does these 3-bit and 4-bit means. Check that out. So for any combinations of wires starting with X and starting with Y, the sum of those two bits represent should be produced as a binary number of wires starting with Z. For example, if you have an addition system with 4 X wires and 4 Y wires, you should be able to supply any 4-bit numbers on X wire and any 4-bit number on Y wires, and eventually find the sum of those two numbers as a 5-bit number on Z wire. So it is saying, like, if you have, let's say, another 4-bit number and Y03, it should give us a correct answer no matter if it is a 4-bit number 03 and 04 or a 5-bit number when we do that. So one of the many ways you can provide numbers to such a system would be to pass 1 1 on wire X and 1 0 1 1 in binary, and so 11 on X wires, which is 1 0 1 1, and 13 on wires Y, which is 1 1 0 1. So let's do a dry run of this as well, just like we did this calculation. So it is saying that we are doing addition of 13 plus 11. In decimal numbers, we know that it is 24. But if we do it in binary summation, so it is 1011 plus 1101. And if we do this, we can see 1 plus 1, 0. You carry 1 here. 1 plus 1, another 0. You carry 1 here. 1 plus 0 plus 1, 1 plus 1, another 0. You carry 1 here. And now this is tricky because you have 3 1s here. So 1 plus 1 is 0. And you carry 1 here, and 0 plus 1 is 1. And then you carry 1 here. And if we see, this should give us exactly. So this should give us 1 1 0 0 0. And if I try to calculate this, this becomes my binary number. So 0 1 2 3 4, which is 16 plus 8 plus 0 plus 0 plus 0. I am very good at doing quick calculation, which comes up to 24, which is correct. So this is how like an ideal calculation should be, where if these are the inputs, our puzzle should give this, our logic should give this output, the logic of gates that we did the whole topological sort in the part 1. And okay, sounds good. And we are doing 0 0 is the least significant bit, and then 0 3 is the most significant bit. And we should get this answer like this, where we should get Z04, 03, 02, 01 as 1 1 0 0 0, which is 1 1 0 0 0. Unfortunately, your actual system needs to add numbers with many more bits, therefore has many more wires that we saw in our puzzle input. So based on forensic analysis of scuff marks and scratches on the device, you can tell that there are exactly 4 pair of gates whose output wires have been swapped. Okay, a gate can only be in at most one such pair. No gate's output was swapped multiple times. Oh, very interesting. So it is saying that why this is giving a wrong answer is because there is 4 pairs of gates that have been swapped. And let's see, what does that mean? I have an idea, but I want to see an example. It's always better to have an example to explain a concept. And it is saying that a gate can only be in at most one such pair. No gate's output was swapped multiple times. So of course, so like we can, all these 4 pair of gates, it's what it's saying is like all these 4 pair of gates will be unique. So, or in simple ways, there will be no repetition. So it's not like you can swap one gate multiple times. Okay. So they are given an example to us. Let's read that. For example, the system below is supposed to find the bitwise AND of 6-bit numbers x0 to x5 and 6-bit number y0 to y5, and then write the result as a 6-bit number on z0 through z05. And if I copy this here, so we are given this example here, and if I read this, we are given one binary number which is x0 to x5, which is, let's say, A, or let's say X, and then we are given another number which is Y, and this is a 6-bit number. And then we are doing some calculations here to get the output of Z, which is also a 6-bit number, it seems like, because we have Z0 to Z5, but in this example, 2 pair of gates have had their output wire swapped, causing the system to produce wrong results. So the first pair of the gates is x0, y0 to 0, 5, and then 0, 5, 0, 5 to 0, 0. And the second pair is 0, 1, 0, 1 to 0, 2, and 0 to 0 to 0, 1. Ah, I see. So if I choose a different color, we can see that x0, 0 and y0, 0 is giving us a value of z0, 5, and similarly x0, 5 and y0, 5 is giving us a value of z0, 0. So this is a gate that has been swapped together. So if I draw a line here, we can see that these have been swapped. And similarly, if I take this one, you can see that z02 and z01, they have also been swapped together. So this gives us two pairs. And if we were to swap back together, it will fix our solution where this will be like this, where 0, 0 is 0, 0, 0, 1, 0, 1, 0, 2, 0, 2, and so on. Okay, so in this example, two pair of gates have output that are involved in a swap, which are marked with the green and the blue color here. And by sorting their output wire names and joining them with commas, the list of wires involved in swap is Z00, 01, 02, and 05. I see. So we are taking all these wires that were part of the whole swap of this two pairs. And if we write them alphabetically, it becomes Z00, Z01, Z02, and Z05. And this is our answer. This is what we have to calculate. Let's read on. Of course, your actual system is much more complex than this. We have seen that. And the gates that need their output swapped could be anywhere, not just attached to the wire starting with Z, of course. If you were to determine that you need to swap output wires AA with EE, OOO with Z99, BBB with CC, and AOC with Z24, your answer would be, so here I think we have taken all these wires and then have done the same thing that we did. Here we have sorted them in an alphabetical order and then we are just doing an output with a CSV value. Your system of gates and wires has four, so similarly how there were two pairs in our puzzle input, we have four pairs that are swapped, due to which our answer is incorrect. And which means the four paired means 8 wires in total. Makes sense. Determine which four pairs of gates needs their output swapped so that your system correctly performs addition. And what do you get if you sort the names of 8 wires involved in a swap and then join those names together with a comma? And I have a feeling that it is going to be an Easter egg. Just like the last one, we had like code kata in the last question. You can see it right here. But yeah, to me, the question is clear, but and I understand this is a fairly complex and fairly interesting question. And it seems like this is a classic debugging problem. And as a software engineer, you will have a lot of times when you will have to debug a system where you will have some kind of an input that is going through some kind of a black box operation and is giving some output. But the problem is that this output is incorrect. And then you have to debug and find like what's wrong in the box by going deep into the code and trying multiple different inputs and test case and see how it works. But yeah, now is a good time for you to pause and think like, how are you planning to approach this problem? And once you're back, I will discuss some of the hints and approach that I am thinking of doing this and see like what are all the things that we can salvage and reuse from about part 1. So I will see you in a bit. And yeah, if you're looking for some hints, let's discuss that. This part 2 is a bit of a interesting question. So I think one of the first things where we have to talk about is that think about how that we will systematically test different combinations. And I mentioned above that this is like a debugging question and where we are given a set of a logic that is adding two type of numbers. And interesting thing is I already talked about like what are the 4 type of cases that we have when we try to do summation binary. I think this is very important in trying to find those gates where the wires have been swapped. And what I'm thinking is like looking at our puzzle input, we can see that Y44 and X44, that it's essentially a 44-bit adder that we are trying to build. And if you see, like if you ran the part 1, we got some answer So part 1, we had an answer that we converted it to binary, but if we converted back, that we converted to decimal, but if we convert it back to binary, I think that is a good point to start with. And then what we can do is we can take our input and do like x plus y ourselves now that we know what are the rules, and then we can get the correct answer. I think doing a comparison between these two numbers is a good place to start. And if I had to explain how the adder looks like, I think probably it's time we do that. So full adder schematic. Let's see, let's go to images. And which one should I pick? I think this one looks fairly simple. So if I copy this image and get it back in our whiteboard, so you can see this is how a full 2-bit full adder looks like. And oh man, this is my like high school computer science all over again. And this is very interesting. If you have never looked into it, I think this gives you a whole new perspective into how everything works. But this is a 2-bit adder that we are given. And this adder is very interesting, where it takes 2 bits and it takes an optional carry in, and then it gives you a sum and a carry out. And what I would like you to do is I would like you to do a dry run on this one with respect to our inputs that we were discussing. So remember, I created a truth table. Let me create that again. So 0, 0, 0, 1, 1, 0, and 1, 1, where I mentioned that 0, 0 gives you 0. And this is AND operation, or like sum. Actually, not, let's not say AND. Let's say sum operation. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, but 1 plus 1 is 0. And we do like a carry in for 1. And we can simulate that to see here if this is correct or not. So let's take the first example where A is 0, B is 0, and C is 0 that we are doing here. And if you see exclusive OR, so exclusive OR is always correct when both the input and output are same. I think I mentioned, question mentioned that somewhere here. So if you see that XOR gets output 1 if the inputs are different, and it gives 1 if inputs are same, it gives 0. So when inputs are same, it responds 0. So we will get a 0 here. And look at these wires carefully. It can be a little confusing. So we got a 0 here, and our carry in is a 0. So we have another 0 here. So when you give 0, 0, if XOR, again, if your both input and output are same, the output is 0. And if you see here, we have a bunch of 2 AND gates as well. So A is coming here and B is coming here. So 0 and 0 will give you 0. And if you see C, carry in is coming here as an input, and your result of A XOR B is coming here as an input, where it was 0. So 0 and 0 is 0, and this is 0. And this is an easy case, right? But I think similarly 0, 1, if we want to quickly see that, let me write that down. So let's say we are doing 0, 1, 0. You can see 0 and 1 XOR, because they are different, it will give us 1. And your carry in is coming from here is 0. And then this is also different, 1 and 0. So our sum would be 1, which is correct. And if you go down on the carry, this is 0 and this is 1. So 0 and this is 1. So 1 and 0 is 0. And here we have A and B, which is 0 and 1. And 0 and 1 is 0. And then we come here, the 0, 0 is also 0. So our carry out is 0. And now looking at the last case, which was, and similarly 1, 0 would be same, but 1, 1 is interesting just to understand how these logical gates are working. So if this is 1 and this is 1, and your carry in is initially 0. So 1 XOR 1 would give us 0. And then this is 0. Because if they are same, the XOR gates exclusive OR gives you 0, and 0 XOR 0 will also give you 0, as you can see here. And if we simulate this, so this is the carry in which was 0 and the XOR which was 0. So 0 and 0 is still 0. But here we have A and B, which is 1 and 1, which gives you 1. And 0 or 1 gives you 1, which is this. So you can see how if we arrange these logical gates in such a way, we can make like a full adder. So this is a full adder. And this is for only 2 bits, but if you have to make it work for multiple bits, you can see how you can just put this in series here, and then whenever you get like a sum out, uh, you take the carry out, and then you use that for your next bit in the location, and then you carry out becomes here. So you can see that you can plug this ABC back here, and then you can add more bits on top of that. And this is how a lot of big number operations happen. And now we looked at our question, and puzzle input states that this is a 44-bit adder. So since the core functionality of the circuit is at binary addition, and now we know how the binary addition works, I think by comparing these two values, where our part one answer and actual answer is incorrect, what I'm thinking is that this is one of those days questions where we generated, remember that Christmas image within the chaos. But here I'm thinking is that I'm going to do some kind of a reverse engineering, because when we compare our part one binary answer and let's say the actual binary, we can find out what are the bits that are incorrect. And by finding the bits that are actually giving us an incorrect answer, since we know the schematics of our full adder, we can actually reverse engineer to find. So we can, instead of going left to right, like first example where we did a topological sort, I think we can go right to left to find out which gate is introducing an error. And on that level, try to find all such gates and try to then swap them and run and see if it helps or not. And this might seem incredibly manual initially. I think it would be really important for us to be able to do that on puzzle output before being able to write a code. Because let's face it, if you want to do a brute force, while that might technically be possible, but that would mean like finding 4 pairs across all the calculations. It will probably take a lot of time. And we can try to do that where we take all 4 pairs that exist and try to swap them and then run this function again and again and again and see if it gives us the correct answer, because essentially you have to match these two answers. These two answers should be equal. And yeah, looking at the question, yeah, so I think also whenever you swap it, the problem is that in our puzzle input, we are only given two 44-bit number like X and Y. But as we saw here in the test cases, that there can be some multiple examples. So I think to verify this thing, like we have to have some kind of a process where to verify that if you have found these 4 pairs, you need to create some synthetic test cases of your own with these edge cases, especially where you are doing some kind of a carry to ensure that your answer is correct. And obviously the simple ones first and then the more complex ones. And yeah, so I think it is basically looking at us on how this combination of AND, OR, and XOR gates work to add each bit position and how the carry happens, and then it will be possibly be able to do that. But I can't think of a systematic and logical way to do it just yet. So I think what I'm going to do is I'm going to put on my thinking cap. And this seems like a fairly difficult question to do programmatically directly without doing bunch of reverse engineering and understanding how it can happen, because those swaps can be anywhere and they don't have to be on the same level as well. And of course, I think I'm also inclined to take my puzzle input and do some kind of a visualization by creating like this chart and then comparing it with my schematics that is given here. Maybe that will also help me find that manually, and then maybe I can work my way through writing some code for that. But yeah, that's all I have in the current thinking process. But with that, I'm going to leave you to also think a bit. So you can pause the video here, think how you will give it a go. And yeah, once we are back and we have the answer for part 2, we will do a quick retro to see how we did. So all the best. And hey, welcome back. As you can see, finally, after 2 hours spending on this, I have figured out the answer and I have solved the part 2 of day 24. And this was a really, really difficult debugging problem, as I mentioned here. And since we were dealing with a 44-bit adder, I tried a bunch of approach, and I initially did as I said here. I got the answer from part 1, converted that to binary, and then I did my own binary calculation using the x and y that were given to me in puzzle input to find out like what are some of the bits that are throwing up an error. And in the next step, I wrote some code with the help of Claude to help generate, take my input, and using the pie graph viz, generate this full blown graph of like how this adder is working at. And then I could see some anomalies in some of the parts. So here and here there is an anomaly, and then here there is an anomaly. But just to make it simple to understand what are the gates that are causing a problem, using that code where I was finding the difference between my bits. So this gave me like faulty bits that were causing a problem. I was able to look at this picture and find the faulty gates, which gave me 4 places where there was some error that was happening on those bits. And after that, I did a bunch of hit and trial where I did some backtracking and then compared my gate arrangement with these schematics. And finally, after trying for the 4th example, I was able to find the answer. Sadly, this is one of the roughest way I solved the problem, and I'm not very proud of this day. But I did manage to reverse engineer it. But I kept thinking after that on how I can write a more programmatic and systematic way to do this. But I haven't been able to figure that out, and I'm honestly very tired. So probably what I'll do is after my challenge is over, because I have day 25 to go with, I'm going to come back to this day 24 question, and I'm going to try to find out how I can write a bit more systematic code. And I have a theory and an example that if I can encode this diagram here that is given here, if I can encode this, so I can encode a FA full adder schematics and then run it through my puzzle input, I should be able to figure that out, because those output gates that we swapped, I could see even in this example that there was some anomaly that was going on here and here based on just like a quick eyeball at the gate and looking at the schematics. But it's a bit overwhelming to do it manually. So I think I'm going to find a way to do it in a more systematic way and then find the answer. But yeah, with this, we are at end of day 24. And we have just one more problem left to go for Advent of Code. And I hope today was helpful. I think this was one of the most difficult days in a way that because I just could not think on how to write some code to do it. Of course, I was able to solve it and debug the problem. And often in software engineering, I think when you are debugging some things, I think doing the manual debug to find the bug and fix it is the first step. And then trying to see how that does not happen and the regression does not happen again is the second step. I'm going to loop back to it, but I'm just too tired right now and I really need to sleep. But yeah, with that, I think if you like this video, consider subscribing and joining our awesome community of developers below. And do share this videos with your friends who are also solving these challenges, and they may find this whole spoiler-free behind-the-scenes discussions of problem solving helpful. And with this, I will see you in the next video. Take care. Bye-bye.